Hello and welcome to the presentation of our paper on hierarchical network and service coordination. As you can see, this is joint work together with my colleagues from Paderborn University. So let's get started with the scenario and motivation of this work. Here we're in a wired networking scenario where we have distributed nodes that are interconnected by links, and each of these nodes may have some kind of limited compute capacity, for example here in terms of CPU cores, and each link also has a capacity in terms of maximum data rate, here 10 GB per second, and has a propagation delay here 5 milliseconds. Now we also have our service or services, and whether we're now talking about virtual network functions in network function virtualization, or microservices in a service mesh, or even machine learning functions in a pipeline, we often have services that consist of multiple chain components. In the example here, I just have a firewall and a deep packet inspection, and then two auxiliary components to indicate the start and the end of this service. And then lastly, I also have traffic that arrives at the network, for example, from our users that want to use these services. And the traffic arrives here at our ingress node. So for example, here at V1, goes to our egress node here at V11 and has a given data rate here 5 GB per second. And now in order to provide these services to our users, we need to scale the involved service components. We need to place instances of these components at the different nodes in the network. And then we need to balance the load across these different placed instances and route the traffic across the different paths that we have. So for example, let's start by putting these auxiliary components at the ingress and egress node, and then we can decide how we want to scale our firewall and deep packet inspection. So for example, we could place two instances of the firewall and one instance of the deep packet inspection. Then we can decide how we want to balance the load between these two instances. And lastly, we also need to decide how we want to route the traffic. So for example, up here along this path, and then down here along this path. And there are a lot of different options that we can choose from when scaling, placing, load balancing, and routing. And when we optimize all of that, we focus in the example here on minimizing the number of placed instances, for example, to reduce licensing costs, and on minimizing the delay that we have in order to improve service quality. So this whole network and service coordination is quite challenging because there are so many influencing factors that we need to consider. All the characteristics from the network, from the services, from the traffic. There are interdependencies between these different aspects of scaling, placement, load balancing, routing, and of course everything keeps changing, so we need to re-optimize whenever something changes. And for this reason, that's really a topic of ongoing research because it's so challenging. If you look at existing examples, most existing work proposes centralized approaches that require a global view and control of the entire network, and then leverage this global view to find highly optimized solutions. And that works well for small scenarios like the one we have here, or probably a bit larger as well. But what happens if we look at quite a bit or much larger networks, for example, like we have them in practice, then even the centralized monitoring and the centralized control become challenging from a technical perspective, but also the underlying optimization problem becomes more and more complex as the size of the network grows and we make centralized decisions. And so with a larger and larger network, these centralized approaches become slower and slower and eventually intractable. And that's a conceptual issue with centralized approaches, not just limited to mixed integer linear programs, but applies to all kinds of centralized approaches. And so a simple alternative that is often also proposed are distributed approaches where we simply take the large network and split it into smaller clusters of nodes, and I call them domains here. And so if the network size increases, we just add more domains, but we can still coordinate within each domain independently and with low complexity. The problem with that is that we don't have real good coordination between the different domains here. And so overall, if you look at existing centralized approaches, they often find very good solutions with high quality, but at the cost of bad scalability or long runtimes. And then if you look at distributed approaches, those are a lot more scalable and faster, but they don't necessarily find good solutions if they don't coordinate between the different domains. And so what we propose is a hierarchical approach where we try to combine the benefits from both centralized and distributed approaches to find solutions with good quality, but also short runtime and good scalability. So let's have a look at how our proposed hierarchical approach works. Start with the design and the design goals that we had in mind here. So first of all, we wanted to make sure that we can support any given hierarchical structure. So here we don't make the decision ourselves how to split the network into domains and hierarchies, but we assume that this is done a priori based on either node locality or based on business aspects. But we want to make sure that whatever the decision is, we can support it. So not just 2 levels of hierarchy or 3, but any number of hierarchies, any given clustering of the network into domains and hierarchies. Then given this information about the network, we want to make sure that we can find solutions with good quality by guiding the coordination between the domains. So that's exactly what differentiates our approach from the distributed approach, is that we guide the coordination between domains. And we want to make sure that we have a solution that scales well by hiding complexity and by ensuring that we can parallelize coordination somehow between the different domains. There are, of course, additional challenges that come with this. So if we say we want to hide complexity, that means we need to hide information, unnecessary information. But at the same time, we also need to make sure that we still give enough information to higher hierarchical levels so they can make good coordination decisions. And then again, we have a trade-off when it comes to coordination, where we have to make sure that we guide coordination by using this hierarchical view, but on the other hand, we need to ensure that this guidance doesn't restrict us too much and that we can still find valid solutions later on. And so overall, what we propose is a hierarchical approach that consists of 2 phases, where we start with, in the first phase, with a bottom-up information advertisement phase, and then second with a top-down coordination phase. So I understand if this sounds very abstract and maybe a bit confusing, so let's have a look at these 2 phases in more detail and also look at examples for that. So let's start with the first phase, the bottom-up information advertisement phase. So let's go back to the scenario. So we have this hierarchical structure where our domains, these groups of nodes, really don't necessarily consist of physical substrate nodes, but possibly also of subdomains themselves. And then these subdomains, again, may recursively consist of more subdomains. We really don't want to know all the details from all of these subdomains, because then we have, again, this huge complexity. And so that means we need to somehow aggregate and simplify information from our lower level subdomains. And again, the question is how much or how do we advertise this information? And here we want to make sure that we advertise enough and important information to make good coordination decisions. But at the same time, we want to hide unnecessary details and simplify this information to ensure scalability. And what we eventually decided to advertise from these lower level domains is the following. So first of all, information about our ingress, egress, and border nodes within each domain. The border nodes are here shown in yellow. These nodes interconnect a domain to another domain, and so these different node types are specifically relevant for routing, and that's why we advertise them. In addition to that, we need to advertise what we call intra-domain paths, so these paths between the different advertised nodes, and then also the inter-domain links, so the links between the different domains. Now, as we aggregate these multiple nodes to intra-domain paths, so for example, these 2 intermediate nodes, they're just hidden and they're just shown as one path. So these paths include compute nodes. We also need to annotate these paths with some additional information. And so these paths are annotated with aggregated compute resources and some extra constraints here. They're annotated with the data rate along the bottleneck link on that path, and they're annotated with the delay on that path. So let's look at an example to better understand how that works. So we're back at the initial network and we're in phase 1, and let's look at just domain D1 and see what we need to advertise here. So first of all, the nodes that we need to advertise are ingress, egress, and border nodes. We have the ingress node over here. We don't have an egress node here, but we have these 2 border nodes. So these 3 nodes is what we need to advertise. In addition to that, we need to advertise the intra-domain paths between these different nodes. And for that, we need to compute all the different paths that we have, for example, from our ingress node V1 to this domain over here. And we do that using or solving the maximum flow problem. And then one path that we get is, for example, the path P1 here to border node V5. And So when we find this path, we need to annotate it with additional information, as I said. We annotate it with the bottleneck data rate link, with the total delay along that path, and with the aggregated compute resources along these 4 nodes over here. Then we continue with the next paths that we find, for example, here P2 via this border node V6, and we again annotate this with additional information about the bottleneck rate, the delay, and the aggregated compute resources along these 4 nodes. And now if you paid attention, maybe you noticed that this aggregated information about the compute resources counts the compute resources at node V4 and V1 twice because the paths overlap here. If we just aggregate this information as such and advertise it to the next higher domain, the next higher coordinator will think that we have a lot more resources than we really have, will overestimate the resources, and we might run into problems here. So what we do instead is we advertise also an additional constraint here that says, hey, we actually share compute resources on these 2 paths, and we share specifically here 10 CPU cores. And so that helps solve this problem. So overall, we repeat doing this with all the other paths that we have within that domain and also for all the other domains, and we can do that in parallel. And in the end, we identify all our ingress, egress, and border nodes, and we can omit all the other intermediate nodes and just replace them with these annotated paths. And so even in this small toy example, you can really say that we kind of drastically simplified the topology here, reduced the complexity, and you can imagine that for larger, more practical networks where we have larger domains, we also have more intermediate nodes that we can completely avoid and omit, and where this aggregation is really powerful to reduce complexity. So the next question is, how can we use this reduced or simplified information for the next phase for coordination? So in this phase 2, we look at top-down coordination, and here again we have some design principles. So as I mentioned earlier, we want to make sure that this top-down coordination uses this hierarchical view to guide coordination within, but also among and across different subdomains to really find better solutions here. And as we guide coordination, we make some coarse-grained decisions, and we help our lower-level coordinators to push them into the right direction, but at the same time, we cannot reduce the decision space too much to ensure that we can still find valid solutions. And we do this top-down coordination starting at the top coordinator up here, and we use this simplified advertised information that we just talked about to make quite coarse-grained decisions. And now remember, these higher-level coordinators, or in each hierarchy, we just see information in terms of intradomain paths with some aggregated information, and these paths represent paths with links and nodes. And therefore, we need to make our placement decisions not on individual nodes, but on these different paths. So that's the difference compared to most existing placement algorithms. And specifically, we solve this placement on our different paths by solving a mixed integer linear program that we also formulated. And that's in the paper, but I won't bother you with the details of that MLP during the talk today. So either way, by solving this MLP, we get a solution for the current hierarchy. We apply that solution and we go one step downwards to the next lower hierarchy, where we then refine this coordination decision. We use the more fine-grained information that we have in the lower hierarchy to refine that decision. And what we do specifically is we take the initial request and we split it into sub-requests that we then solve in each subdomain in parallel. So for example, if we decide, hey, place an instance of component 1 here and of component 2 here, then inside this domain, we only need to consider coordinating component 1, but not coordinating component 2. And we continue with this coordination in a recursive manner. So again, let's have a look at how this works in an example. So again, we're back at our network with the aggregate information. We have our source and destination over here. And now we need to think about how to do this coordination. And on the highest level, we might decide, let's put our firewall instances on these 2 paths and our DPI instances on these 2 paths. And then we need to decide the load balancing. We might say from the 5 GB per second that are arriving at the source, we balance the load like this. And then we decide the routing along these different paths. Now, this is the high-level coarse-grained decision that we have, and now we go one hierarchy downwards and refine this decision in the lower hierarchies. And for that, let's just have a look at the domain at the top right here. So what this domain sees as an input from the higher level hierarchy is that traffic arrives with 3 GB per second at the border node here and with 2 GB per second at the border node here, and that we need the DPI somewhere here. And so the sub-request that this domain has to solve only contains the DPI, but not the firewall. The firewall was in another domain, so we really don't have to worry about that anymore. And that's what reduces the complexity here when doing this top-down coordination. So if we now zoom into this domain and do the coordination on that domain, we have some more information about the involved nodes, and we can do the placement on these nodes now. So again, we have as sources now the 2 border nodes, and the destination is here the egress. And we might decide that we just need one DPI that's shared by traffic from these 2 sources. Yeah, and that's how we do the top-down coordination. Of course, we still also need to do the routing here and so on. But that's in principle how it works. So overall, our hierarchical coordination approach consists of these 2 phases, the bottom-up information advertisement and then the top-down coordination. And the main idea is that we can ensure the quality of our approach through this global view that we have at higher hierarchical levels, but also ensure scalability by reducing the complexity that we have when going between these hierarchical levels, and by parallelizing coordination between the different domains. So we implemented a prototype of this hierarchical approach and evaluated that on a real-world network called Janos from the SND-lib library with 39 nodes and 122 links. We looked at 2 different services and at randomized traffic arriving at different ingress nodes. And we compared 3 different approaches in our evaluation. First of all, a centralized approach that's indicated by k = 1. And the centralized approach is like a normal approach. It finds globally optimal solutions, but it looks at all the nodes at once and coordinates the entire network at once. And then we looked at 2 hierarchical approaches, one with 2 hierarchical levels indicated by k = 2, and then one with 3 hierarchical levels indicated by k = 3. And we first looked at the solution quality, where we considered 2 different metrics of interest. First of all, the number of instances that are placed, and that's what we want to minimize. And here 4 scenarios with increasing load, so with more and more requests. And as you can see, the centralized approach with k = 1 finds optimal solutions. That's just how it is. But as you can also see that our hierarchical approaches find solutions that are very close to optimal here. If we have more hierarchical levels, so k = 2 and then k = 3, the solution quality gets slightly worse because we have more aggregation and more hidden information with more hierarchies, but we're still very close to optimal here. And the same goes if we look at the other metric that we wanted to minimize, which is the total delay. It's also optimal in the centralized approach, but again, our hierarchical approaches are very close. And so overall, with more hierarchies, we have more aggregation of information, so slightly less information available, so that leads to slightly reduced quality, but still both of these hierarchical approaches find solutions that are very close to optimal. Now, let's have a look at the runtime, because there's always 2 sides to everything. And here we can see that, again, for increasing load, the runtime here in seconds on a log scale, in general, solving a mixed integer linear program is slow. But you can see that the centralized approach is much, much slower than our hierarchical approaches. That's because with these hierarchies, and the more hierarchies we have, the more we can reduce the complexity and the faster our solutions are. And so here with k = 2, with 2 hierarchies, we are 88% faster on average than the centralized approach. And with 3 hierarchies, k = 3, we are 470% faster than the centralized approach on average. So that's really great. But there's a but. You can also see that the runtime grows faster for our hierarchical approaches. And that's a problem. And that's because for our hierarchical approaches, complexity grows in 2 ways. First of all, if we have more requests, so that's a larger input. But we also have more ingress and egress nodes because these requests may arrive at new nodes. That means we need to advertise more nodes. That means we need to compute more paths between these nodes. And if we have more paths, we also have a larger decision space, and that's what makes our whole problem slower. And we looked into this a bit further, and we thought, how can we overcome this problem? So basically we need to reduce the number of advertised paths, because by default we advertise all the paths that we find by solving our max flow problem. Those can be really a lot of different paths, even for the same source and destination pair. So if we limit this number of advertised paths, then we have a smaller decision space, lower complexity, and our approaches should be faster. And so we looked at the hierarchical approach with k equals 3, advertising either all paths, or just 2 paths, or just 1 path. We found that, of course, if we reduce this decision space or this information, our quality here in terms of number of place instances gets a tiny bit worse, but that's just 2% on average here. But if you look at the runtime, we can have huge improvements by reducing the amount of advertised paths. So for example, here advertising 1 path compared to all paths, the purple versus the green, gives us a speed up of 3.4, so 340% in average, and we're, with this approach, more than 10 times faster than the centralized approach. And so overall, advertising less information only slightly decreases the solution quality, but it drastically reduces complexity and improves scalability. And that brings me to the conclusion of our work, where you saw how our hierarchical approach works with the 2 phases, the bottom-up information advertisement and the top-down coordination. In the evaluation, we saw that we can find close to optimal solutions, but are much faster than a typical or an equivalent centralized approach. And we saw how we can navigate this trade-off between quality and scalability by controlling the number of hierarchies that we have, and by controlling the amount of advertised information. So, for example, advertised paths that we give in our approach. So overall, with this hierarchical coordination approach, we can combine the benefits of centralized and of distributed approaches. I think that's a very useful framework in general to improve performance and scalability also of existing approaches. And yeah, if you're interested, all the code is publicly available on GitHub. Feel free to check it out. Thank you for listening.